Hello everyone. This is our second part of our lecture associated with looking at t-test. This second portion of our lecture is going to be examining at the very important issue associated with related samples t-test. Now, one of the big differences that we find between related samples t-test and independent samples t-test is that, remember, with independent samples t-test, we are using different individuals in the two different groups. So in other words, people who are in group 1 are different from individuals who are in group 2. So thus we're using a between groups research design, and that naturally is going to have a little bit more error variance that we're going to have within our analysis. And the reason for that is that because since we are using different individuals in group 1 versus in group 2, we're naturally creating differences between them. The way that we kind of solve this particular issue is by using a within groups research design, and thus using statistical analyses that are what we call related samples, or even what we sometimes call paired samples t-test. So essentially here with the related samples or a paired samples t-test, ultimately what we're doing is we are taking the same individuals and we're using them in both groups, or we are looking at a pre-test assessment and then we're looking at a post-test assessment after an intervention or a treatment occurs to examine now if individuals have changed their scores from pre-test to post-test based on some manipulation. So here, in this particular instance, let's use our example that we use in our independent samples t-test that we're using smokers versus non-smokers. Let's say that people started off as non-smokers and we were testing them on exam performance, and then we ended up giving them the treatment that was actually them smoking. So now that we've given them cigarettes, that we've given them the nicotine, that drug, now we examine their scores again. So using the same individuals. So in that particular case, if we were using the same individuals in both groups, we would end up using a related samples t-test rather than an independent samples t-test because it would be the same individuals. But in that previous example with an independent samples t-test, we were using different individuals to represent the different groups. So here we're using the same individuals to represent both groups. The only difference between them is the different manipulations that they're experiencing, or potentially that something happened in between an observation and a treatment. So we always think of a pretest as being an observation. So here, think of the way that we would actually do this is that we would say an observation, which would be my pretest, right? Then we would have a treatment occur, which would be my manipulation, for instance. And then we would have our post-test, which would be my second observation. Okay, so what we want to determine are scores changing from here to here because of this potential factor. So in other words, is the treatment having an effect on the dependent variable at time 2 or at post-test in comparison to that of pre-test? And since we're using the same individuals, here we have to change our statistical analysis. We cannot use an independent samples t-test because that assumes that the individuals are mutually exclusive or the groups are mutually exclusive, but rather here they are related to each other, thus being the same individuals. Now, what I've posted on Blackboard for you, I've posted up this diagram, and I know that this kind of popped up just out of nowhere, and you're kind of looking at it going, okay, what is this? This is ultimately what we call a decision-making tree. So one of the things that we're looking at from here on out this semester is we're looking at all the different analyses that we're going to be able to use in terms of trying to identify what's really best for us in terms of the statistical analysis that we want to use. So what's the best statistical analysis that we have available for our purposes in terms of our research questions or in terms of how we've designed our experiment? So you'll notice here that at the top it says purpose of the statistical analysis, and then we can go in different directions. So you'll notice here if we go to the left it says summarizing univariate data, exploring relationships between variables. We are going to be talking about these types of statistical tests a little bit later on in the semester. So we have statistical tests like the Pearson's product moment correlation coefficient, which is my R stat. We're going to be talking about that a little bit later on. I'm going to introduce for you chi-square later on in the semester. So we're going to talk about these different types of analyses, the looking at the relationships portion towards the end of the semester. For our purposes right now, we're really in this area here that we're looking at test differences. So in other words, we're looking to see if groups significantly differ. Those groups being related to each other or not being related to each other, it doesn't really matter, but we're going to go down this branch because that's what we're really examining at this point. We're looking at group differences. So now you'll notice here that we have under the testing of significant differences the number of groups. So one of the things that I mentioned to you is that with t-test, let that be independent samples or related samples, we're always dealing with two groups. So you'll notice here we have the option for our two groups. So here for our two groups, different types of tests, you'll notice that now we have the independent samples t-test, and then we also have a related samples t-test. So here, with our related samples t-test or our independent samples t-test, you'll notice that we finally get to the point where we say, okay, this is the type of statistical analysis that we're doing because we have groups that are mutually exclusive from each other, or we have groups that are related to each other. So under the groups that are mutually exclusive or independent from each other, we finally come down to the point where we talk about the independent samples t-test, where we have interval or ratio data being used. With our related samples t-test, we now go down to this portion here. If we talk again about interval or ratio data, we're talking about paired samples t-test in this particular case. So here, this is the major difference between the two. So using this type of decision-making tree is going to be very helpful for us for the remainder of the semester and for the remainder of your statistical careers or research careers, because this is a very useful technique for deciding for yourself what kind of statistical test do I really need to use to be able to answer the research question that I have or that I've actually posed in this particular research situation. So here, when we think about this aspect of groups being related to each other, in many instances, when we begin thinking about statistical analyses, the very first statistic that we always begin to introduce is the independent samples t-test. So we start ingraining in our students many times that, oh, you know, you have these mutually exclusive groups, you're comparing these individuals who are different from each other. But one of the questions that normally arises is, well, is there a possibility that we can actually have groups that are related to each other? And the answer is absolutely. We definitely can have that. We can have individuals being used in both of our groups that are the same individuals, or we're looking at their pre-test versus post-test differences. So in that case, rather than using an independent samples t-test that would allow us to compare different individuals who are in different groups, we're now using the same individuals across both groups. So here, for instance, let's think of a situation that we would want to set up for this, that we would say to ourselves, okay, well, let's look at comparing individuals in terms of when they receive an online strategy. So let's say, for instance, at the beginning of the semester, we're going to develop an online strategy guide for our statistics students. So at the beginning of the semester, I give you a little statistics exam, like a little mini quiz at the beginning of the semester, and I get your baseline understanding of statistical analyses. So out of there, let's say, for instance, that you score a value of a 2 out of 10, right? So you get 20% of the material correct on that pre-test assessment because you don't have any level of knowledge associated with statistics, or you have a very minimal level of knowledge of statistics. Now, as the semester progresses, we start providing you with online strategy guides. So in other words, we start giving you all the information online, everything is completely online, and we really don't do anything that would be textbook related or anything like that. It's just online lectures and online videos and online study guides and online this, but the textbook wouldn't have anything to do with the class. So now we want to compare the performance from the pre-test assessment, you know, those 2 out of 10, right? That average that individuals got, 2 out of 10 or 20% as an average for pre-test. Now we want to look at their post-test scores. So after they've used that online strategy guide, do their scores change, or do their scores remain the same, or do their scores increase or decrease? What happens? So here, using a related samples t-test is going to allow us to be able to answer this type of question that we say to ourselves, okay, well, what's happening to our data once it is that we include this manipulation and we're using the same individuals to compare across the groups? So in other words, when I compare individuals from pre-test to post-test, are their scores changing? Are they staying the same? What's happening? That's really the question that we're trying to get at this particular point. So when we look at our formula for a related samples t-test, this is what our formula looks like. Now this looks like a lot more like a simplified version associated with our independent samples t-test, but there are some core differences here that we do find with our related samples t-test. One of the core differences that we find with our related samples t-test formula is that our related samples t-test formula assumes that we are using the same individuals across both groups, or from pre-test to post-test, whatever the case may be. So whatever group it is that you consider to be group 1, that's always going to be your pre-test. Whatever group it is that you consider to be group 2, that's going to be your post-test. So one of the key issues here that the formula for a related samples t-test is going to be using, if we look at our numerator here, Again, in our numerator, we always have effect variance. So this is effect. Oops. That's effect. And this is our error variance in our denominator. So we still have the exact same conceptual formula for both statistical analyses, for our t-test that is independent samples, and also for our related samples t-test, that we have effect in the numerator, error in the denominator. Now you'll notice here that there are new statistics that are being introduced here, that we have this statistic here, that's our D. What does D represent? D represents the difference that we actually have, and this is the difference from post-test to pretest. So post minus pretest. Okay, and this is a very, very important issue that we need to consider whenever it is that we're actually calculating our scores, that we always take post-test scores minus pretest. We never take pre minus post. So you'll notice in the examples that we're going to be using for this lecture, I'm always going to talk about post-test minus pre-test scores in terms of calculating my difference. So that's what our D value represents in terms of our statistical formula. We also have, in terms of our statistical formula, D squared. So it's essentially the differences between our scores. So in that particular case, we're going to be squaring our scores, the difference of our scores in that particular instance. We also introduce here our portion of our formula that is the sum of our difference, and then we are going to square that that sum. So here, this is very, very different from this portion of our formula, so be very careful with that. In one of our instances, we are first going to sum up all of our difference values, and then we're going to square them. In other instances, we have our difference values, we're going to square them first and then sum them up. So we're going to see how to actually do this in terms of our calculations for our specific statistic. We also have our sample size that we're already very familiar with. So sample size is nothing different in this particular case. And here we also have our degrees of freedom, but you'll notice here our degrees of freedom for this particular type of statistic, for our related samples statistic, that our degrees of freedom are not n minus 2 as we had with our independent samples statistic, but here we have n minus 1. And here we only deduct n minus 1, since again we are assuming that they're the same individuals across the two groups. So here it really wouldn't be fair for us to deduct 1 from each group, since they are the same individuals. So rather our formula requires us only to use n minus 1 as our degrees of freedom. So that changes just a little bit between our independent samples and our related samples t-test formulas. So remember that with independent samples t-test formula, we always take n total minus 2. Here we take n total minus 1. And what does n refer to? N refers to the number of paired observations. So the number of paired observations. So in other words, let's say that you have 25 participants. Essentially, n refers to 25 in that particular case because you have 25 pairs of observations. So for participant 1, they did pre-test, post-test. All the way through participant 25, they all did pre-test, post-test. So the number of paired observations would be 25, thus equaling our sample size of 25 in that particular case. But let's say that you had 25 individuals come into your study, but only 24 of them gave you both pre-test and post-test, then your n would be equal to 24 because you couldn't use that 25th participant who didn't provide you with that information. And that's a key issue here that we have to think about in terms of using our related samples t-test, is that we have to make sure that individuals give you both scores. And that was something I mentioned on the previous slide, that we have to have individuals give you both scores on that same measure. So they have to give you both scores. They have to give you pre-test and post-test, or they have to be in group 1 and also in group 2. They just can't be in one or the other. So if they only give you pre but they don't give you post, you can't use them. If they don't do pre and they do post, you can't use them either. Because in that instance, you have nobody to really compare them to. And again, the issue here is that we're comparing their scores to their scores across both groups or across both pre-test and post-test in those specific situations. All right, so let's look at a sample data set here. I've taken this directly from the chapter reading that I posted online for you. And again, remember, I would prefer for you guys to use that chapter reading that I provided for you rather than the one from the textbook, because I feel that this is a much more simplified version of understanding our related samples t-test than that what's given in our textbook. Now again here I just do make a note for you to make sure that when you do calculate the differences, the difference score, or D, is going to be the difference between post-test minus pre-test. So we're always going to subtract pre-test from our post-test scores. So that's why in certain differences here, in certain situations, we have positive values. So in our particular case, for instance, if you would take pre-test minus post-test, so subtract 7 from 3, you would technically get a -4, but here that's why we get a +4, because we're using post-test minus pre-test in this specific instance. So here what I've done for you is I've provided you with two columns. Our first column is all our pre-test. Our post-test has its own separate column. We have a difference column, and then we also have a d-squared column. So here what we're going to do is the very first step that we want to do in terms of our formula is we want to calculate sample size, or we want to calculate the number of paired observations that we have. So in terms of sample size, we're going to count these up, and if I recall correctly, we should have 25 paired samples, or 25 participants who participated in our study. So each one of these rows represents one person. So we have 1 through 25 in our particular case. So we know that n minus 1, our degrees of freedom, are going to be equal to 24. Okay, and remember, because in this particular case we use n minus 1, not n minus 2, and that's very, very important for us. The next portion that we need to calculate is we need to calculate our d value for each one of our pairs. So in other words, we need to calculate the difference between pretest and posttest for every single paired observation. So here the difference between a 7 and a 3 is a 4, 8 and 5 is 3, 6 and 4 is 2, 7 and 6 is 1, 8 and 5 is 3, 9 and 5 is 4, 6 and 4 is 2, 6 and 5 is 1, 7 and 3 is 4, 8 and 6 is 2, 8 and 7 is 1, 7 and 8 is -1, 9 and 7 is 2, 10 and 6 is 4, 9 and 7 is 2, 9 and 8 is 1, 8 and 8 is 0, 8 and 9 is -1, 4 and 9 is -5, 4 and 8 is -4, 5 and 7 is -2, 6 and 7 is -1, 9 and 6 is 3, 8 and 7 is 1, 12 and 8 is 4. So here we have all our different scores for every single paired observation. So we here have, this is my D column that we have in terms of my statistic. That's my D column in this particular case. So the next portion of our equation, so we already know what our D value is going to be for every single paired observation. So we want to take the sum of D in this particular case. So our sum of D in our particular case is adding up all of these values, and it's okay that we have some positive and we have some negative values. That's not a problem. We're going to go ahead and sum them all up, and we're going to have a sum of D equaling a value of 30. Okay, so that's the sum of D in our particular case. So sum of D is equal to 30. That's the numerator in my formula. Okay, so now we're going to continue on with our formula, and we're going to look at the following piece of that formula. So again, looking at our denominator, we need to know our sample size. We know that we need to take now the sum of D squared. So in other words, we're going to take every single difference value and we're going to square it. And then we need to subtract that product we're going to subtract that product by the sum of D, and then we're going to square that value. So our value of 30 that we already have for the sum of D that we have in our numerator, that we have in our numerator, we're now going to square that value, okay, in this particular case. And then we also know that in our denominator we have a value of a 24 because we knew what our sample size was -1. So in this particular case, it's going to be 24. So again, looking here in our particular case, we know now that the sum of D is going to be equal to a value of a 30. So again, in my numerator, I have a value of a 30. That's my sum of D. So now let's continue working with the next portion, that we now need to take the square of every single difference. So here 4 squared is 16, 3 squared is 9, 2 squared is 4, 1 squared is 1, and we continue on down the line all the way until we get to our very last difference value of 4. So 4 squared is going to be 16. So once it is that we've done that sum, or that we have all of those D values squared, now we're going to take the sum of those D values squared. So again, remember that in my formula, it said the sum of D squared. So we first do D squared, and now we add up all those D squares. So here, in our particular case, my D squared is equal to a value. So we've taken the sum of d squared in our particular case is going to be a value of 180 in this particular case. But remember, in my formula, it asked me for n times the sum of d squared. So in other words, we've already calculated the sum of d squared, but we need to make sure that we still multiply this times our value of 25, which is the number of paired observations that I have. Now, once it is that we know that value, we're going to subtract that times the sum of d that we have in this particular column, because remember, this was the sum of d in this particular situation that our piece of our formula is asking for, but now we're going to square that value. So we already know what the sum of d was equal to. It was equal to a value of a 30, and we're going to square that value. So in our particular case, if we take 25 times 180, so 25 times 180 is going to give you a value of 4,500 minus 30 squared, which will give you 900. So now 4,500 minus 900 will equal a value of 3,600. Divide that by 24. Because remember, in the denominator of our formula, it still requested that we had this part of the equation divided by degrees of freedom, so n minus 1. So in our particular case, divided by 24. So 3,600 divided by 24 is going to equal a value of 150. Okay, so that's now in my denominator, but remember, our formula also requested that we needed to take the square root of that value. So I still need to take the square root of 150. So go ahead and do that. So taking the square root of 150, and that should now give you a value equal to a 12.24. So in my numerator, I have a value of 30. In my denominator, I have a value of 12.24. So now we complete our equation by taking our value of 30 divided by 12.24, and that now gives me a value of t that is equal to a value of positive 2.45 once we round off to the second decimal point. So there's my statistic, a value of 2.45. So remember, in our equation, the first part that we need to do is always calculate sample size. In this particular case, the number of paired observations that we had 25 for our sample size. We know what degrees of freedom are in this particular case because it's n minus 1, so we were able to calculate that value, so that gives me a value of a 24. That's going to be the denominator of the fraction that's in the denominator of our formula. Now we have to take the sum of our differences, or first we have to calculate our differences. Remember, that's post-test minus pre-test to give us all our values. Then we take the sum of those values. That's going to be my numerator. So in our particular case, it was a value of a 30. That's my numerator in my formula. That's my effect variance. We're going to divide that now by, in our particular formula, the sum of d squared. So all our difference values, we're going to square those difference values. Once we sum up those difference values in this part of our formula, we come up to a value of a 180, and we multiply that times my sample size because that's what's requested by my formula. Remember, my sample size was equal to 25, so 180 times 25 equals 4,500. Our second portion of our formula for our denominator requested that we take the sum of d and square that. So we took the sum of our d values, which was a value of a 30, and now we square that value, giving me a value of 900. So 4,500 minus 900 gives me 3,600. We divide that now by our denominator of n minus 1, our degrees of freedom, so giving me a value of 150. We then take the square root of 150 because that's the last part of our formula that we're required to do, giving me a value of 12.24 in my denominator. So we take our value of a 30, which again is my effect variance. My denominator of 12.24 is my error variance that I have in my formula, and giving me a t-value of 2.45. So that's all great and dandy, right? So you're like, great, awesome. So I calculated a value of 2.45 for my statistic. What do I do now? As you guys can imagine, what's the next step that we have to take? We have to do null hypothesis significance testing, right? That's what we have to do. So null hypothesis significance testing. So in our particular case, we're going to do our statistical testing just as we did with our independent samples t-test. So we use still the same critical value table because this is still the critical value table for t. It's just a different type of t, but it's still a t. So here it's okay to use the exact same critical value table. So in our particular case, again, our distribution is going to be a normal distribution that we have. Again, the mean for that normal distribution is going to be a value of a 0 because this is where the null hypothesis is true. Right? We talked about this when we talked about our Z formula and we introduced null hypothesis significance testing. In our particular case, I want to do a two-tailed test. And in my two-tailed test, I want to have an alpha level of 0.05. Okay, so 0.05 two-tailed test. So here's my two-tailed test, 0.05. And now I'm going to go down to 24 degrees of freedom because remember, in this particular case, degrees of freedom were equal to n minus 1. So we had 25 minus 1 equaling a value of a 24. So here we're going to look at row 24, column 0.05 alpha level, two-tailed test, and we find that my critical value is a 2.06. Now since it is a two-tailed test, remember that we have to have a positive and a negative 2.06 in our particular case. So here we're going to draw 2.06 positive and negative 2.06. So in our case, our statistic was equal to a value of 2.45 positive. So our statistic lands right here in the region of rejection. So it lands right there inside the region of rejection because remember, all of this portion is my region of rejection. So in this particular case, what conclusion do I draw about the differences between pre-test and post-test according to my data? So here, since my stat lands in the region of rejection, so it's in the region of rejection, I'm going to reject the null hypothesis. Because remember, my stat landed inside the region of rejection. So here, the conclusion that I'm going to draw is that the alternative must be true, and I'm going to accept that statement made by the alternative hypothesis that the groups do differ. So here, what do the null and the alternative hypothesis predict associated with the related samples t-test? It predicts the exact same thing as it did with an independent samples t-test, that the difference between group 1 minus group 2, so here, group 1 minus group 2 was going to be equal to 0. That's what the null predicts. The alternative predicts that mu1 minus mu2 would not be equal to 0. So in other words, we just now replace this with pre-test, post-test, right? So rather than us saying mu1 and mu2, we're just going to use the words pre-test and post-test for our specific example here. So in other words, the null predicted that there should be no difference between pre-test and post-test scores for these individuals, no matter what the treatment was. The alternative predicts that there should be a difference between pre-test and post-test for these individuals based on the treatment. Here in our case, we've rejected the null hypothesis because my statistic landed in the region of rejection. Thus, I've now concluded that the alternative must be true and the null hypothesis is false. So I do conclude that there is a difference between pre-test and post-test scores for individuals. So setting this back up with our example that we had on one of the previous slides, does using a technique such as online study guides or strategy guides help students perform better at post-test? And the answer is yes. Yes, it does in this particular case, because we see that scores did increase from pre-test to post-test in this particular case. So we do find that there is a significant difference in that instance. Now, many times you're going to encounter while reading a research article or reading a textbook in some instances, or even reading your statistics textbook this semester, you're going to find that in many instances you're going to have statistics that are given to you. And all that's going to say is it's going to say the statistical analysis that was conducted was an independent samples t-test or a related samples t-test, and this is what we found. And it's going to say a t-value equal to negative 2.45, comma, p less than 0.05. And you're going to say to yourself, well, what does that mean? So how do I interpret a value that is a t-value of 2.45 with a p-value less than 0.05? And that's a very important issue that we have to address in terms of how it is that we read results, in terms of statistical information that's given to us in journal articles, specifically. So let's say, for instance, we're looking at an independent samples t-test, and you were to encounter the following situation. And we find that we have a t-value, and then you have open parenthesis 8, close parenthesis, equals negative 4.94, p less than 0.05. So how do we read this information, right? That's a good question. And the answer is the following. This is how we would interpret it. There is a significant difference that existed between the two groups which were compared. So how do we know that? How do we know that there was a significant difference between the two groups? Because I'm going to look here at my p-value. Because remember, I talked about this when we talked about null hypothesis significance testing, that we use the standard p greater than or equal to 0.05, you're going to retain the null, right? If p is less than 0.05, we're going to reject the null. So in other words, we're going to say that the groups do differ. So in our particular case here, we find that there's a p-value less than 0.05. So you're probably asking yourself, well, how do I know then that that statistic actually landed in the region of rejection? And again, this goes back to something that I talked about in the previous weeks, that I told you, very rarely, if ever, are you actually going to do this stuff by hand and actually go to a critical value table, find your critical values, see if your statistic lands in the region of rejection, and then conclude, okay, yes, it did land in the region of rejection, so I've rejected the null hypothesis. I do find that there are significant differences between the groups. Rather, in many instances, what you're going to do is you're going to put data into a computer, you're going to analyze the data, and it's going to pop up a result, and the result's going to look just like this that I have here for you. So rather than it's showing you that your stat landed in the region of rejection, all it's going to give you, the t-value and a p-value. And then you have to draw conclusions from this information. So here we draw the conclusion that the groups do significantly differ. Now, if you're asking yourself, okay, so you taught us this entire process and you didn't teach us how to do this in a computer, and the answer is yes. I definitely did not show you how to do it yet in a computer, because that's really reserved for other courses that you're going to take in the future. So for instance, when you guys take research methods or you take an advanced statistics class, those are things that you will do at that point, that you will actually take programs such as SPSS and use them for those purposes to be able to analyze data in those specific instances. So here for our purposes, we're still learning the theory, we're learning the conceptual purposes associated with our formula, so it's important for us to do that. But in many instances, when you take other classes, you're going to be reading research articles and you need to know how to interpret this data that's given to you in a results section. So rather than just getting to the results section and skipping it because you're like, it's a bunch of numbers, I'm just going to skip to the discussion, now you can actually look at the statistics and you can say, okay, they did find significant differences, or they did not find significant differences according to their statistics. Now you're probably asking yourself, okay, what's that number that's in the parentheses? That's a good question. This is my degrees of freedom. So if you remember from our independent samples t-test lecture, we had a sample size equal to 10. So n was equal to 10 in that particular case, but we took n minus 1 for group 1 and n minus 1 for group 2, and that left us with degrees of freedom equaling 8. That's why in parentheses here we have the value of an 8. So here, the way that we always format our statistic is we have our lowercase t value, or our lowercase t symbol, in this case our letter t, space, open parenthesis, my degrees of freedom, close parenthesis, equals my t-stat that I calculated, comma, my p, my letter p is actually in italics, and then I write less than or greater than 0.05. In this particular case, because my statistic landed in the region of rejection, I'm going to say it's less than 0.05, because that matches up with the conclusion that we're going to reject the null hypothesis. Now, what happens in the case where you find something like this? That it says t, open parenthesis 20, close parenthesis, equals negative 0.2, p less than 0.05. So here, the interpretation that we would make based on this standard that we have here with p greater than or equal to 0.05 or less than 0.05, we're going to now read the p-value that's here, and the interpretation we would make is there are no significant differences that existed between the two groups. So here in our particular case, we also know that or that our sample size was equal to 22. And how do I know that? Because remember that for an independent samples t-test, we always have n minus 2 as my degrees of freedom. So if I want to know what my sample size is, I'm going to take my degrees of freedom and add 2. In this particular case, 20 plus 2 is going to be equal to 22 in that particular case. So thus my degrees of freedom are equal to 20. That was my t-value, negative 0.2, very close to 0, p greater than 0.05. So that seems to match up with the idea that my statistic was so close to 0, there's probably no significant differences between those groups in terms of the two averages. Now, for a related samples t-test, you may encounter something that looks like the following. So in our particular case, with the example that we just completed, we would format our results as follows. T, again, lowercase t, open parenthesis, my degrees of freedom. Now remember, for related samples, my degrees of freedom are always n minus 1. So in our particular case, we took sample size, which was 25 minus 1 to give us 24, equals my statistic and my p-value associated with my stat. So remember, in our previous, in this example that we were using, we said that my stat of 2.45 landed in the region of rejection with the two-tailed test alpha level set at 0.05. So here we rejected the null hypothesis. Thus, p-value would be set at less than 0.05 because that suggests that the probability that my statistic of 2.45 was less than 5%. So it occurred due to chance less than 5%. I'm going to be allowed to reject the null hypothesis in that particular case. So here we say there are significant differences between pre-test and post-test scores, or between group 1 and group 2 using the same individuals. Okay, and that's the key since it's a related samples, that we're using the same individuals. In the case where we were to find something that looks like the following, t open parenthesis 38 equals 0.32, p greater than 0.05, here we would conclude there are no significant differences between pre and post-test scores, or that there are no significant differences between group 1 and group 2 using the same individuals. So here, how do we know that there is no significant difference? Because again, we look at the p-value. My p-value is greater than 0.05, and in this case, I'm going to retain the null hypothesis, and again, my null hypothesis predicts that there's no difference. So here I have to conclude that there's no significant difference. Now, in our particular case, for our sample size, for our particular example here with 38 degrees of freedom would be equal to 39. Because remember, we have our sample size minus 1 would be equal to the whatever values here in parenthesis. So we take degrees of freedom plus 1 in our related samples t-test, and that will give us the number of paired observations, or the number of the sample size that we're actually dealing with in that particular case. Now that wraps up our discussion associated with t-test. So we've now covered independent samples t-test and related samples t-test, both statistical analyses, which are very, very important and commonly used statistical analyses in psychology and the behavioral sciences, and they're very useful techniques even in other disciplines like computer science or engineering, or other disciplines even like marketing, where you want to get people's assessments of user-friendly technologies, or is my computer program being more effective once I change the programming code. So when we were using this specific programming code, these were the values. Now I've changed the code, and now these are my new values that I get. If I compare those scores, am I doing any better? So you can use these types of statistical analyses in those specific instances. I hope the lecture has been helpful in terms of clarifying and really trying to understand what independent samples t-test and related samples t-test are and what they're used for in statistical testing. Please make sure also to read the chapter readings that are provided for you online, because those are very, very good. They're going to be very helpful chapters in terms of understanding what they're used for. If you want to go ahead and read the chapters that are also in your textbook, you can definitely do that. I unfortunately think they're probably going to leave you with more questions than answers. So I would strongly suggest really using the chapters that I've given you online. Please also remember to turn in your homework by this Friday, and again, it's due by 11:59 p.m. Have a good rest of your week, and we are approaching the end of the semester. It's coming up very, very quickly, and I do hope that everyone has been enjoying the class up to this point.